PCB Foundations, by Paul Taubman and Sean Kelly. Presented by 9.Connects. Chapter 2. PCB Fabrication Overview. 2.1 Introduction. Before we begin to design a PCB, we must understand the physical structure of the PCB. Remember that we are designing something that is going to be manufactured. In the PCB manufacturing flow, there are two major processes: fabrication and assembly. The term fabrication is used to describe the creation of the printed circuit board. In mature technology companies that have been around for decades, they only use the term PCB, printed circuit board, in conversation, as a general reference. What they officially use, in their documentation and revision control systems, is the term PWB, printed wiring board. This acronym indicates a board that has been fabricated, but has not been populated with components. In conversation, a PWB may also be referred to as a bare board. After the bare board has been fabricated, it is given to an assembler. The purpose of this operation is to attach components to the board. This is generally referred to as the PWA, printed wiring assembly. Throughout the PCB literature, one may come across the use of PCB referring to the bare board, and printed circuit assembly, PCA, referring to the completed assembly. Another nomenclature commonly used by contract manufacturers is PCB and PCBA, in which the PCB is referring to the bare board, and the PCBA is referring to an assembled board. In many companies, separate revision numbers are issued for the PWB and PWA. This allows the company to make and modify two different manufacturing documentation sets under different revisions. For example, if the PWA documentation requires modification, the PWB documentation set can be left alone. More details about the manufacturing documentation will be presented in later chapters. 2.2 The modern PCB. The most common configuration of a modern PCB is a stack of conductive copper layers separated by dielectric, insulating layers. These can range from a simple 2 conductive layer stack-up to 18 or more conductive layers. Conduction paths between layers are routed with the use of vias. Vias are copper-plated holes that extend through specific layers of the PCB and provide the vertical conduction path for the traces from layer to layer. The top and bottom layers of a PCB are where the electronic components are attached to the board, using various soldering techniques. Although there are technologies that allow for embedding components between inner layers, we will only be discussing the more common ways that PCBs are designed and manufactured. 2.3 Why understand the fabrication process? It is an unfortunate fact that anyone can create a PCB in an EDA, electronic design automation, tool that cannot be manufactured. Although EDA tools have design rules that can help guide the design along, the individual creating the design needs to know the fabrication process, in addition to knowing how to use the tool. By the way, the term electronic design automation is a misnomer. Quite frankly, there isn't that much automation going on. That is why there is still a great need for PCB layout designers, who understand the requirements and pitfalls of the entire PCB fabrication and assembly process. It cannot be emphasized enough that one of the best ways to help in your education of the PCB process is to become very acquainted with your board fabricator. Visiting a fabricator and receiving a tour is extremely helpful in understanding the process. Most fabricators are more than happy to show you their facilities and talk with you about their capabilities. An understanding of the process itself is a benefit for both parties, and minimizes much of the back and forth conversations and unnecessary delays during the board design and fabrication. In the long run, a good relationship with your fabricator will save you time and money, let alone stress and headaches. 2.4 Layers of the stack-up. A PCB is typically made up of 4 different types of layer materials: copper, prepreg, core, and solder mask. In order to grasp the fabrication process, the layer stack-up must be understood. 2.4.1 Dielectric material. The insulating material that exists in between the copper layers is referred to as dielectric material. Dielectric materials are further broken down into core and prepreg, which will be discussed later. There are many different dielectric materials. The most common is the FR4, or FR408, board material. The FR stands for flame retardant, which means that a component may catch on fire, but the board will not, though the smoke is rather noxious. As for the number 4, this is a material type classification, which is defined as an epoxy resin with a glass fiber cloth base. FR4 is a grade of material, and does not specify a brand per se. If material is specified only as FR4, any number of materials can be substituted. But FR4 is so common, that most fabricators use it as a baseline for their equipment and processes. If you do not specify a particular dielectric, or require a specific impedance, the fabricator will use their favorite FR4 grade material by default. Though most PCBs are green in color, the color is due to the solder mask that is applied to the top and bottom layers. FR4 and other dielectric materials tend to be white, yellowish, or brownish in color. Other materials are available that present different dielectric properties, better isolation, mechanical strength or flexibility, and characteristics that can aid in the performance of specialized circuit applications. The decision on the proper dielectric material must be decided, based on balancing/optimizing design performance, versus cost requirements. 2.4.2 Core. A typical core is made up of two copper foil sheets, separated by a hardened insulative material between them. Whereas the copper on a PCB is used for connectivity, the material used between the copper layers is used for electrical isolation, dielectric properties, and mechanical stability. The core material comes in several standard thicknesses, in a range of around 4 mils to 60 mils. Non-standard thicknesses can be created as well, but at high potential cost and long lead times. Standard copper foil thicknesses are usually specified in ounces, meaning the weight of 1 square foot of the copper foil. More about copper thicknesses will be discussed later in the chapter. 2.4.3 Prepreg. For boards containing more than 2 layers, several cores can be combined. This is the purpose of the prepreg. Unlike core material that is already hardened and covered with copper, the prepreg is a mushy material that is more pliable. It consists of an uncured resin and a glass weave. If a 4-layer board is desired, the fabricator will place the prepreg between 2 core layers. Under both heat and pressure, the resin of the prepreg will bond the 2 cores together. Once this process is complete, known as curing, the prepreg will be as hard as the core material. In fact, after the curing process, and assuming that the same dielectric material was used for both the core and prepreg, the prepreg and core are indistinguishable. 2.4.4 Combining core and prepreg. There are several ways to combine core and prepreg. For example, another process for a 4-layer board is starting with a core material that will represent layers 2 and 3, and then using a prepreg layer above and below the core, followed by a copper foil on the top and bottom. In this setup, the copper on the top and bottom core, layers 2 and 3, would be etched first. The prepreg and foil would be added after. Finally, after the curing process, the copper foil on the top and bottom would be etched. The concept of copper etching will be explained in detail later in the chapter. Notice that in both methods of layer stacking described above, copper layers are built up in even numbers. In the past, a one-sided board was a common practice. Traditionally speaking, the top layer may be referred to as the component layer. This is a throwback to the days in which components were only placed on the top of the board. Conversely, the bottom layer was known as the solder layer, not to be confused with the solder mask. Prior to current technology, the components contained long leads that would be bent, threaded through the board, and soldered on the bottom side. The excess lead length would be cut off after soldering. With the use of surface-mounted components, and the number of traces that need to be routed, one-sided boards are no longer practical for most applications. One-sided boards can still be found in power supplies, and other electronics using large components, to handle the wattage of the power system. A surface-mounted component is a component which is soldered to the surface of the board. With modern PCB manufacturing processes, boards can be populated with components and routed on both sides of the board. Beyond a two-layer board, it makes little sense to have an odd number of layers. For example, it will cost the same to fabricate a three-layer board, as it would with a four-layer board. The fabricator is simply going to etch off all the copper on one side of the core. More importantly, the rule of thumb in fabrication is symmetry. Without a symmetry of layers, the board will be subject to warping, and a warped board cannot be assembled with components. As for the number of layers one can have, the limit is set by the fabricator's machinery. In all practicality, it is unlikely that one will have to create a board that is more than 18 copper layers. A product with such a layer count will be in the thousands of dollars to recoup the manufacturing costs. Granted, this is not uncommon for military hardware or high-end servers. However, the consumer market will not tolerate such prices. The most common stack-up is the two-layer board, with a four-layer board being a close second. In high-speed design, 8 layers provide an optimal base configuration. 2.5. Dielectric materials. There are many different dielectric materials. As mentioned previously, the most common is the FR4 or FR408 board material, and is so common that most fabricators use it as a baseline for their equipment and processes. FR4 does have limitations, and may not work for some special applications. Dielectric materials have important characteristics that must be considered. Here are just a few to be aware of when designing a PCB, which is why your fabricator should be consulted prior to designing. Dielectric constant, or relative permittivity, dK or ER, is a very important factor in high-speed designs. The dielectric constant of a material varies over frequency, and usually decreases as the frequency increases. Materials suited for high-frequency applications are those that the dielectric constant remains relatively constant over the entire operating range. Dielectric loss tangent, or dissipation factor, delta symbol or dF, gives a measure of the power lost due to the material. This can be a factor in both very high-speed digital circuits, as well as sensitive analog circuits. Electrical strength is the measure of how well of an insulator the material is. In very high voltage applications, it is extremely important for the material to resist the movement of electric charge through it. Coefficient of thermal expansion is the expansion rate of the material over temperature. This can be an important factor during extreme temperature environments that the PCB might be exposed to, during operation or a special manufacturing process. Other factors need to be researched and considered as well. 2.6. Solder mask. Although FR4 and other dielectric materials tend to be yellowish or brownish in color, most finished PCBs have a green, red, or black color to them, green being the most common. This color is due to the solder mask that is applied to the top and bottom layers. Solder mask has several purposes. First, it protects the copper from degradation and corrosion caused by the environment, especially moisture and humidity. Copper is prone to reacting with other metals and elements in the air. For example, the color of the Statue of Liberty is turquoise, due to its copper construction reacting with the salty air. Long-term exposure may result in decreased functionality, or complete failure of the board. Second, and most importantly, the solder mask acts as a dam during reflow, melting of solder, when adding components to the board. Without the solder mask, the solder could wick along a copper trace, or run down a via, rather than creating a proper bond between the component and pad. The traditional color used for the solder mask has been green. Oddly enough, the exact historical reason for the green color is not completely known. Some claim that it was a requirement of the U.S. military, since the color provided an excellent contrast to the components. Others claim that it was the byproduct of the chemicals being formulated when they were developing the solder mask, that it might have been a concerted effort to make the PCB more appealing, or that the color of the board represented the stage of the design. For example, red was used for prototyping, and green was used for production. With the advent of liquid photosensitive ink, LPI, any color of solder mask can be produced. Keep in mind that the color does impact the dielectric constant, and that the cost will be higher for custom colors. If the PCB is going to be hidden under the covers of an enclosure, it makes little sense to change the color. EDA tools automatically create this mask as part of the way it handles footprints for the components, although the user has the ability to add, adjust, or even remove them as desired. 2.7 Copper in detail. Now that we have some basic understanding of the PCB stackup, including the pre-preg, core, and solder mask layers, let's explore the copper aspects of the stackup a bit further. In the EDA tool, signal layers are drawn by the designer, and include copper pads, traces, and any other copper feature that is required. Shown below is a two-layer PCB, with the red traces being on the top layer, and the blue traces being on the bottom layer. In between these two conductive layers is the insulative core material. Although the copper is drawn for each layer in the EDA layout tool, the fabrication process is a negative one, meaning that the fabricator starts with a full layer of copper, and then etches out the copper that is not a part of the design. It is like the story about Michelangelo, who was once asked how he was able to turn a block of marble into a sculpture of David. He replied, "You just chip away the stone that doesn't look like David." Fortunately, the documentation functions within the EDA tools, and the fabrication equipment will handle the creation of the negatives used for etching. The designer simply needs to draw it as they envision the final product. In both the EDA tools and the fabrication process, the layer count is based on the number of copper layers, and does not take into consideration the dielectric materials. For example, a 4-layer PCB would consist of 4 copper layers, 3 dielectric layers, which could be 2 cores in pre-preg, or 1 core and 2 pre-preg, and the solder mask layer for the top and bottom of the board. As mentioned earlier, we start with a copper foil on both sides of the core material, and then etch out the copper that is not part of our design, using a photoresist and chemical process. In the EDA tools, the designer can declare a copper layer to be a signal layer, or a plain layer. A signal layer is generally used to provide connections between components. In most cases, the top and bottom copper layers are always signal layers, to accommodate component footprints. The one exception is when the bottom layer is used as a power plane when the top has the space to handle all the components. In addition to connecting the signals together, power and ground must be provided to the components. A network of copper traces could be used for this purpose, but this adds to the trace count, which in turn makes it more difficult to route all the signals to and from the components. In high-speed design, copper is required either directly above and or below the signal trace, to reduce current loop impedance in the return path. Failure to do so will result in major signal integrity issues. Therefore, it is a common practice to declare certain layers to be planes. These planes are mostly solid copper, with perhaps some copper removed to allow for several isolated sections on the same layer, or to isolate vias that are passing through the layer. Most EDA tools treat these plane layers as a negative image, meaning that if a layer is declared as a plane, any shape drawn on the layer represents copper to be removed. By contrast, signal layers are always drawn as a positive image, even if the fabricator uses a negative process to remove copper. Therefore, in a layer stackup, you may see the terms signal, plane, component, and solder layers. This provides references to understand the PCB stackup. To the fabricator, a copper layer is a copper layer. The copper itself can be of different thicknesses, and is defined as ounces per square foot. Oddly enough, it is the global industry convention to define copper thickness in ounces, instead of mils or millimeters. The use of ounces to define thickness comes from the process used to make the copper foil, and describes how much copper is used to cover 1 square foot of surface area. Copper weights typically come in one of 3 thicknesses: 1 ounce, 1.4 mil thick, 1/2 ounce, 0.7 mil thick, and 2 ounce, 2.8 mil thick. A completed PCB could have any combination of all 3. Most often, the PCB will have 1 ounce copper on the top and bottom layers, and 1/2 ounce on each of the inner copper layers, although this is not an absolute requirement. As previously mentioned, copper is susceptible to corrosion, and is mostly protected by solder mask. However, the areas of copper that are used for component soldering, and are left exposed after the masking process, require a surface finish that will provide this protection, as well as prepare the surfaces for soldering. This is accomplished by using a plating process that drives another material consideration. Some of the more common plating options are: Hassel, hot air solder leveling, coats the copper with a thin layer of solder. Immersion tin, uses a chemical reaction to plate the copper with tin. ENIG, electroless nickel immersion gold, is a 2-step plating process that uses nickel to prevent gold from migrating into the copper, and gold to provide excellent connectivity. Plating materials change over time, due to better processes and environmental regulatory issues. Discussing the latest plating options with your fabricator will help in making these decisions. 2.8. Vias. Now that we have a better understanding of the layers necessary to create a layer stack-up, we need to provide some details about the copper structure that allows these layers to communicate. A via is a copper-plated hole that allows connectivity from one layer to another. The types of vias used on a PCB depend on the complexity or density of the board, and the packaging technology used for the components. The following is just a brief introduction to the types of vias that are used on modern PCBs. The most common, and least costly type, is the through-hole via. It connects copper from one layer to another, typically in the Z direction. This type of via is drilled and plated after all the lamination processes are complete. The blind via is one that connects the top or bottom layer to some of the internal layers, but does not go all the way through the board. It is blind to the other side of the board. This type of via allows components to be placed on both sides of the board, without reducing the available real estate on the opposite side of the board. The buried via does not extend to the top or the bottom layers of the board, it is buried inside. The micro via is a laser-drilled via that is filled with a conductive epoxy. This is similar to a blind via, with the added advantage of its very small size, 4 to 6 mil hole size range. These are mostly used on high-density/small pitch devices, where larger vias between component footprint pads will not work. The use and type of vias on a PCB play a significant role in the cost, yield, and the time it takes to complete the fabrication. In the example here, an 8-layer board has through-hole vias that allow the routing of a net from any layer to any other layer. It also includes a micro via for routing between layers 1 and 2, a blind via for routing between layers 4 and 7, and a blind via for routing between layers 7 and 8. For a stack-up like this, the fabrication process must add several processes to each core, prior to laminating them together. This includes the drilling of holes, desmearing, the process of using a chemical to remove the prepreg material that may have been smeared over the exposed copper of the annular rings on each layer during drilling, followed by the plating of copper to connect the annular rings. Therefore, the cost of the board is highly dependent upon the number of holes and the number of additional steps that are added to the fabrication process. Micro vias are typically more expensive than through-hole vias, and have potential reliability issues under certain conditions. Using micro vias should be a well-informed and thoughtful decision made by the designer, not a forced decision by the fabricator to salvage an otherwise non-manufacturable board. 2.8.1 Via hole sizes and annular rings. Choosing the correct via hole sizes and annular rings is an important part of the design process. The via hole minimum diameter is dependent on the depth of the hole that will be drilled and plated. The hole must be large enough for the plating process to deposit ample amounts of copper inside of the hole, to allow an uninterrupted conduction path. Fabricators provide a ratio of board thickness to hole size that they are capable of successfully producing. For example, a 10:1 ratio would mean a 0.063-inch thick PCB can have a minimum of a 0.0063-inch, 6.3 mm, hole. In addition to the hole size, the annular ring size must be chosen as well. The annular ring is the copper pad that is included around the hole, to connect the via to the trace on any layer that the trace is routed on. The via hole is not always perfectly drilled in the center of the annular ring. Having a larger annular ring allows for more variation in drill location, without the risk of breaking the conductive path to the trace. However, having too large of an annular ring limits the routing paths, and increases the spaces needed between vias and holes in the PCB. In addition to the tolerances of the drilling equipment, to locate the drill in the center of the annular ring on the surface of the PCB, layer registration variability, how well all the copper layers line up during the curing process, will affect where the holes line up on all the other layers. Also, drill wander is a variable that also needs to be considered. Drill wander is due to the size and flexibility of the drill bit, the sharpness of the bit, and how it finds its way through the glass fiber structure of the dielectric material. All these factors need to be considered and discussed with the fabricator, before any routing is accomplished. 2.9. Solder paste. The solder paste layer is not really a layer, per se. It defines the locations of where solder paste needs to be applied. More detail about this layer will be discussed in the chapter pertaining to assembly. For now, it is mentioned because the solder mask and solder paste are confused by many individuals new to the PCB process. With the commercial use of SMT, surface-mounted technology, in the 1980s, the user can now put components on the top and bottom of the board. Instead of using solder, the assembler uses solder paste, which not only acts as a paste to hold the component to the board temporarily during the assembly process, but contains the solder that is used to permanently mount the component when heat is applied to it during assembly. All EDA tools provide the user the ability to create the paste layers that define the solder paste locations on the PCB. However, unlike solder masks, which cover everything except for the copper that needs to be exposed, the paste layers define just the areas for the paste to be applied. While it may seem like the solder mask template could also be used for the solder paste, it is often the case that some sections of the board are not covered with either the solder mask or the solder paste. For example, test points need to have electrical access, but may not have an actual component attached to them. 2.10. Silk screens. One other layer that is part of the fabrication process is overlay, or silk layer. This layer provides human-readable information, such as reference designators for the components. It is called the silk layer because the information on this layer was traditionally silk screened onto the printed circuit board. In the past, this artwork was very useful for the hand soldering of components, and for rework. It also allowed the test engineer to find components very quickly when testing or debugging a PCB. There are disadvantages to the silk layer. Silks take up real estate on the board, which is becoming more precious as the trend is for PCBs to be as small as possible. In addition, the artwork can provide information that allows for reverse engineering of the board, thus allowing for knockoffs of the product. In short, be wise about using the silk. If the board is being produced in a small number for the purposes of proving out the circuit, known as prototyping, it greatly benefits the designer to add this information, as it will speed up the prototyping process. However, if this is going to be mass-produced in a country that does little to protect one's intellectual property, IP, you may want to leave it off altogether. 2.11. Panelization. Up to this point, we have talked about the individual PCB. However, The fabricator does not produce PCBs one at a time. They use predefined panel sizes that allow them to fit multiple iterations of a PCB within that panel. This is known as panelization, or paneling. PCB designers who have in-house fabrication facilities will be expected to handle the panel layout. When using an outside fabrication service, most fabricators would prefer to handle the panelization on their own, since they know their equipment and process. Furthermore, most fabricators are going to panelize boards to minimize material waste. It does behoove the designer, during the PCB groundwork stage, to work with the fabricator to determine the best use of the fabrication area available, if there is a desire to minimize cost. For example, the cost of fabricating 6 boards may be as effective as fabricating 5, since there is room on the panel to accommodate the 6th board. For those designers who have the responsibility of designing the panel, additional information must be presented to the fabricator. The fabrication process needs to include information such as V-scores, also known as V-cut, or locations for a milling drill to separate out the individual boards after fabrication. A panel is generally kept together after fabrication, and is separated into its individual boards after the assembly process. It is far more efficient to assemble components onto a panel, than it is to populate individual boards. 2.12, Chapter Summary. Fabrication is all about putting together layers, that will work together to form the circuit paths that connect the components of the board. Understanding the composition of the layers goes a long way in designing PCBs that can be fabricated without difficulty. The layers that make up a PCB layer stackup were discussed: core, prepreg, solder mask, copper, solder paste, and silks. Each layer, and its aspects, have entire specifications written about them. However, just having a basic understanding of the stackup goes a long way in making a manufacturable PCB. If you are interested in these specifications, it is recommended that you become familiar with the IPC. This organization has been around for many years, and serves as a trade group for the fabricators and assemblers. However, over the years, they have made strides to reach out to the designers, in an effort to educate them on the proper techniques to ensure a successful fabrication and assembly of the PCB. If you are going to invest the time and effort in being a layout designer, it would behoove you to pursue the Certified Interconnect Designer (CID) certificate offered by the IPC. Important tip: get to know your board fabricator and become best friends with their CAM engineer.